So, imagine we have a light source. It's a light source, yay. We're not actually going to be doing stuff with light sources, but it's a good analogy to how flux works. So, if we imagine a bunch of little photons, or not photons, yeah, photons coming out.
Squiggle like that?
They squiggle like because they're in some wave.
Because they're a wave.
It's actually an electromagnetic wave. It's actually an electromagnetic wave, which is crazy. But anyway, my photons are weird, but it doesn't matter. So imagine we have like a ton of photons coming out of our light source in 3 dimensions, but it's just 2 dimensions on the whiteboard. We can call amount of like luminous intensity based on like the density of these photons. So if we take a surface and we close this light source with the surface, like this is a sphere around the light source, you could say that at this point the amount of photons per area, so photons per area, is equal to like the luminous intensity of the light. So if we doubled the size of the sphere here, then we'd have twice the area, or no, 4 times the area. And the luminous intensity would be P over 4A. So it would be, if we call this like luminous intensity 1, this would be luminous intensity 1/4. 4 times the area, 4 times less density and intensity of light. So that's actually exactly how electric field waves, or not waves, just electric field lines work. It's like the same way as these photons. Electric field is actually just a density of total electric flux, which is sort of like easier to visualize with these like physical photons. If you have like this big sphere, the same amount of photons are hitting the sphere, but it's just like at a smaller density, which is what changes the intensity of the light. Cool. So, electric flux is a total amount of like flow of electric field. Flux electric is equal to the dot product of electric field times area for a small amount.
It's easy enough.
If we have a little like area bit and we have a bunch of electric field lines moving through this little area bit, then we could use this to determine how much electric field is flowing through this area. So it's important to remember that the dot product is also just equal to EA cosine theta, which makes this a lot easier because we're not actually doing vector calculus right now, luckily. So for this example, let's say we had an electric field that was uniform and it was 2 newtons per coulomb. Electric field. Roger, you still writing?
I got it.
Okay. And let's say this surface was 2 meters by 2 meters. What would be the electric flux of field going through the surface?
It would be 2 times C.
What's the angle though?
Sorry, the angle is the same.
So they're parallel?
They're parallel.
Okay,
yeah.
so what for?
They're perpendicular.
8.
Sorry, I need to go back and read it right. Area vector, if we have a little piece of area, an area vector is a vector that represents that area and it's orthogonal to the piece of area.
Oh.
So it's like a plane vector?
Yeah, exactly. So the length of the vector is equal to the area of the surface, and the direction of the vector is orthogonal to the little slice of area. And that's why we're using a dot product, because it's like how much the electric field is piercing this amount of area.
So 4 Newton meters squared per coulomb.
4 Newton meters squared per coulomb. 4 is the area, so area equals 4.
Oh shoot, 8 Newton meters squared.
Oh no, Nathan.
Test, student be thought.
2 newtons per coulomb of electric field, 4 meters squared. Cosine is of 0 degrees. Cosine of 0 degrees equals 1.
Wow.
So that's equal to 8 Newton meters squared per coulomb. So that is the electric flux of this little bit of area here.
5.
Yeah, it's a weird unit, but it's just area times field.
Oh, we use it for spherical coordinates.
Meters squared. Meters.
Use what for spherical coordinates?
Pi.
Oh yeah. Yeah, you use Greek symbols for a lot of things. Great, okay. Now let's take another example here. Let's take these same 4 electric field lines. And now our surface is sideways. So this is like a surface like this, the field lines just like going like that. So let's say that this is the exact same surface except now it's stretched. But no, actually, sorry, it's a different surface. It's bigger, but it's tilted, so it's the same height. It's still 2 meters tall and 2 meters wide here.
Oh.
But its hypotenuse, I guess, is 2 root 2 meters. So this is a different surface, but it has the same footprint of this surface. Can you determine the electric flux of the field going through this surface?
Wouldn't it be 2 times 2 times 2 times cosine 45 degrees?
So this is a 45-degree
So
surface.
that would be 2 times 2 times square root 2.
So you have 2 newtons per coulomb
So
times
it's 4
2 meters times 2 root 2
Yeah.
meters
4 root 2.
times cosine of 45 degrees. And what's cosine of 45 degrees?
That's
Root 2 over 2.
So root 2 over 2. Yeah, or 1 over root 2. It's the same thing. So you go to 2 newtons per coulomb times 2 meters squared times 2 root 2 times 1 over root 2. And look,
which is just 4.
these cancel. We have the same
Oh,
A
that's just a
Newton meters squared per coulomb. It's the same amount of electric flux. So when we turn this surface, it doesn't matter that it was facing a different direction, but what does matter is that the same like footprint. So it's the same amount of electric flux. You can imagine like if we had like a water stream here, let's just use 2 dimensions, so we have a bunch of water flowing. If we have like a little dam here, or like a little dam here, it's the same amount of like flow of water that's going through.
Oh.
It doesn't matter the shape of the dam.
Yeah.
Which is kind of cool.
Okay.
So that was just for uniform fields. And it's actually the same for not uniform fields too, which is really cool. Yeah, let's make a little bit of a more formal formula for electric flux. Scratch this. For any curved surface, electric flux is equal to the integral of E vector dot dA. Where dA is a little differential area vector. So that's just equal to integral of E times dA times cosine of theta. However, electric flux is almost always used to completely close off a surface. Typically, electric flux isn't just measured as a little plane here, but it's a sphere or some Gaussian surface which encloses a charge to measure like the total amount of field lines coming off of that charge. So we change this integral symbol by putting a little circle in the middle of it, and that represents a closed integral. It's a closed surface around some object. Yeah, so you can use this for electric flux. You can use EA if it happens to align, or E dot dA. You can also use sum of E dot A if for some reason your surface is like a rectangle. So there's like a bunch of like multiple parts, but you don't have to integrate it. Like if we have 6 surfaces here, our Gaussian surface would just be the sum of all of these 6 surfaces. So a Gaussian surface, Gaussian, is a surface that encloses a piece of charge so we can measure its flux. So we're going to derive another formula for electric flux because there's a third one connected to a Gaussian surface. So we're going to do that with this sphere. All we're going to leave is this. Actually, yeah, we'll leave this. Cool. So we have a charge and this is a charge Q. We're trying to measure the amount of flux that this charge gives off. So we're going to make a Gaussian sphere to enclose the charge. That's a Gaussian spiral, oops. This is just a circle on the paper, or the whiteboard, but it's always a three-dimensional. You don't ever do flux in 2 dimensions because it's inherently a three-dimensional concept. But yeah, you can like do physics, magnetism, and electricity with like just a whiteboard. You know, like all the stuff in 2D. You can like theoretically have like a 2D charge density for everything, and like normal interactions. But with flux, you don't ever have like a Newton meter per Coulomb. You never have that for flux. It's always gonna be 3D. Yeah. Okay, so can anyone figure out what the flux is for this charge? First, we're using this formula here. What's the first step?
Find the area of the surface.
Yeah, but can we simplify this interval? Do we need this to be an interval if it's a sphere? We're going to do the polar coordinates over it? No. So here we have
Can we just make a
cosine theta, right?
surface?
All of our area vectors of the sphere are pointed in the same direction as the
They're all
electric
true.
field.
So you can eliminate cosine theta.
Right, so you can eliminate cosine theta because it's just cosine of 0, which is 1. So drop that. And then also, because the sphere is equally spaced around the charge,
So it's just
the
times
electric field is
circumference.
uniform, yeah. So we just have E times A. Great. Our flux for the surface is just E times A, which is convenient. And a lot of times you'll be using E times A on the exam. They don't want you to do more complicated stuff. So yeah, our flux for this sphere is equal to E times A. And for this case, let's plug in A and E. So we have the surface area of the sphere is just equal to 4 pi r squared by definition of a sphere. And then for E, we're going to use Coulomb's law. So we have electric field is equal to K
Is it
Q
4 or 4/3?
over r squared.
Is it 4? No, you're right.
For surface area.
Oh yeah, the volume is 4/3.
Oh.
Electric field is just K Q over r squared. And here we're actually going to expand K. So we have equals Q over 4 pi permittivity of free space for E squared. You'll see this 4 pi. It's kind of important because when we plug in E times A, we're going to multiply these together. And we're going to end up with r squareds cancel, 4 pi's cancel.
So it's just Q over
And we have equals Q over permittivity of free space. Yeah, it's kind of cool. We typically write enclosed to represent the amount of enclosed charge. So now we have flux equals the integral of the dot product of electric field with area vector is equal to Q enclosed over permittivity of free space. And because we just proved that in a uniform field, if you change your surface, it's going to have the same amount of electric flux. We haven't actually proved yet that this it does the same thing in a not uniform surface, but it actually does. So this is this formula applies to everywhere. Q enclosed over permittivity free space is equal to this. And it's not typically that you'd be using like this formula when you can't use Q enclosed. It's typically you'd be like solving for properties of electric field and area with this electric flux value Q enclosed over epsilon 0. Yeah. So if you imagine like we had a bigger Gaussian surface here, you know, we'd have a different radius, but we'd have the same amount of electric flux. I think it's kind of cool that the definition of electric field like lines, like these arrows, remember how I said last lecture that like the density of the arrows represents like the electric field? That's because we know the electric field density is equal to, or electric flux density is equal to electric field. So like the amount of these arrows is sort of like the electric flux. You could say like the electric flux was, oh, it's 6. I mean, it's not 6, but like 6 arrows here. These same 6 arrows come out here. And we have a higher area, so it's a lower electric field. Yeah.
Oh, I get that.
Yeah, it's the same thing with gravitational field, sound waves. All of these have the inverse square law because of this like sphere. As the sphere gets bigger, you decrease the area and you increase or you decrease the density. So that's why the inverse square law exists. It's because of the sphere. It's not that flux exists because of the inverse square law. It's the other way around. Yeah, okay, so that's fancy. That's how electric flux works. And now we're going to apply it to more problems. So let's say we have a plate. And this plate contains a bunch of positive charges. Yay. This is in 2 dimensions, but let's just draw in 1 dimension. That's what it looks like though. So we have a plate,
Oh, are
a
we on
cross
that?
section of a plate. We're about to get there.
Oh.
We're gonna get there soon. So this plate has some area, it has some charge, and then that also means that it has a charge distribution. So we're gonna determine the electric flux, or the electric field lines this plate gives off using the electric flux definition. So because it's positive, the electric field lines are going to look like this. I guess there's some electric field lines that look like this. But typically when we're considering a plate like this, we're only considering like as if it was a really, really large plate, and we're assuming that most of the points we're going to be measuring are like close to the center and not the edges and are very close to the plate. So yeah, so assuming we have an infinitely large plate here, we're going to measure the electric field given off of it with a Gaussian surface. The Gaussian surface we're going to use is a cube. So the cube is now going to be piercing through this plate. Sorry for the change. So this is going to look like this on our cross section. This is what the Gaussian surface around the plate looks like, and we're going to use this to determine a flux of a small part of the plate and an electric field lines of a small part of the plate. Okay, so let's say that this Gaussian sphere has lengths L, or is a cube, sorry, Gaussian cube. Also could be like here, L, L. So the first step is Q enclosed over E0. So we have some area of the plate here, and we know the charge distribution, the surface charge distribution times area is equal to Q enclosed here. So if we call this space area here, the amount of charge that this Gaussian cube encloses is equal to the area times the charge distribution. Q enclosed, and then we divide all this by permittivity of free space. So our flux value for this Gaussian cube is equal to this. Okay, so now we're going to sum up all of the sides of the Gaussian cube to figure out the other formula for flux, which we can use to derive the electric field around the plate. So we have this is equal to sum of all 6 faces. Nathan, can you
Aren't only two
Can you-
of the faces?
right, exactly. But can you say all 6 faces and the angles that they have with electric field.
What, 90, 90, 90, 90, 0, 0?
But okay, so we have the top one
Well, the top and the bottom have
The
the
top
angle
one,
0,
right.
or,
have the
yeah,
angle 0.
and the rest of it angle 90.
Yeah. So the bottom and top are aligned with the electric field, and on the sides here, these area vectors are going this way. These are 90 degrees and not aligned whatsoever. So pretty much the only faces of this Gaussian cube that matters
The top and
are
bottom.
the top and bottom. And the ones on the front too, don't do anything. Alright. Okay, so we now know that, so it's equal to sum of EA cosine of theta, which is just going to be equal to, in this case, 2EA. We have two faces, and we have the electric field. It's going to be the same on both of them, we're assuming. And the area is equal to the area in the center. So we know that 2EA equals charge distribution times area over epsilon naught. And we can cancel out the a's here. Boop, boop. 2E equals charge distribution over epsilon naught. And now electric field equals charge distribution over 2 epsilon naught. So anywhere in this, or on the edges of the Gaussian surface, that's going to be the electric field value. And the really cool thing about this is, typically, with electric field, like as you get farther away, the electric field is decreasing. But in this situation with this infinitely large two-dimensional plate, it doesn't do that. As we get farther away, we could just theoretically draw another Gaussian surface here. And this is much higher, but these sides aren't affecting it at all. So this is the same area here. And we're gonna have the same electric field anywhere up
Oh,
and down.
yeah.
It's uniform. And you can also see that because when we point all these arrows, they're all pointing in the same direction. They're not like getting more sparse as you go farther apart. So if you're really close to a plate or you're really far, it's actually the same electric field from it because of flux. And you can also prove that by like just doing a double integral with the Coulomb's law, but we don't need to. So yeah, uniform electric field around an infinitely large plate. Obviously, if it's not infinitely large, it's not going to be like that because they're going to start pointing out. Yeah. Okay. So that is how you use electric flux to solve for an electric field value. I should probably just go back over all the formulas from that. We have electric flux is equal to this thing, or it's equal to this thing, or it's just equal to this based on the circumstance. We have all of that is equal to Q enclosed over epsilon naught always. And then we also have for a plate, the electric field is going to be equal to charge distribution over 2 epsilon naught. And that's, you can think of this actually because it's like there's there's electric field lines going up and down from the plate, so that's why we have to split it into 2. But otherwise, it's just like the same as the flux formula.